We are just over 75 years old. We sit on about 5,000 acres. We have over 300 buildings that we maintain, so we're a little science city here out on Long Island.
Two different ways to develop quantum sensing. One which is really directly quantum sensing to intrinsically push the sensitivity. And the other one is more like what Kerstin had said, which falls more in the category of quantum enhanced techniques.
The power is not enough of exascale systems or anything that will come in the near future.
In terms of low-level control, we were able to basically use their APIs to do some experiments to see how we can improve the gate errors. So I think it's maturing, but there's still a lot of research to be done.
Brookhaven, we're always open to collaboration, so if you want to work with us, please do feel free and contact us.
From Orion X in association with Inside HPC, this is the At HPC podcast. Join Shahin Khan and Doug Black as they discuss supercomputing technologies and the applications, markets, and policies that shape them. Thank you for being with us.
Hi, everybody, and hi, Shahin. It's good to be with you. We haven't recorded in about 10 days, so it's great to be back.
It's a delight to be here and really excited about the conversation today with our guests.
Yeah, we thought, it's kind of quantum season, a lot of conferences going on in the quantum computing area. So we have a great trio of folks from Brookhaven National Lab on Long Island, and really excited to talk about quantum computing, HPC, and also quantum networking. And with us, Kerstin Kleese van Dam. Kerstin, if you could give us your title, your role, and a bit of your background.
Yes, Doug and Shahin, it's great to be on this podcast. So my name's Kerstin Kleese van Dam. I'm the director of the Computational Science Initiative at Brookhaven National Lab. And basically, we are responsible for computer science and applied math research at Brookhaven National Lab. And within that, we're also including quantum research in those areas, basically.
And we have Gabriella Carini.
Hello, hi, great to be here. I'm Gabriella Carini, and I'm the Director of Instrumentation Division at Brookhaven National Lab. Instrumentation, as the name suggests, takes the role of developing all sorts of instruments with application on big science, but also, in relation to societal impact type of work and also small companies. So it's a very broad spectrum of activities we have. And quantum is also one area we've been focusing on recently. I'm also been chairing a working group at the lab focused on developing strategies and activity on QIST, quantum science and technology. And as part of that, I coordinate the various activities at the lab and focus specifically on quantum networking. We have developed lots of infrastructure at the lab, several experiments with our key partners at Stony Brook University, our nearby university. And we also have, I would say something more about our quantum network testbed facility and the Long Island quantum network activities in New York.
Okay, wonderful. And thirdly, we have Meifing Lin.
Yeah, hello. Yeah, it's very nice to be here. I am Meifing Lin. I'm leading the high performance computing group at Brookhaven's Computational Science Initiative. So my group does traditional high performance computing, mainly trying to get scientific applications to scale and run efficiently on the large supercomputers we have, the classical supercomputers. But I'm also interested in seeing what quantum computers can do for these scientific applications. So what can quantum do for HPC? And to that end, I've been involved in some physics-oriented research to see what we can do to make the current noisy quantum computers to be more useful for these scientific applications.
All right, brilliant. I think the first question I have, maybe this is Kerstin for you, to tell us a little bit more about Brookhaven. You did announce a few really exciting quantum communication demonstrations and advances and research that I want to ask you about. but maybe a little bit about Brookhaven itself.
Yes, I'm happy to talk about it. The DOE national labs count as the best kept secrets in the US. Brookhaven maybe aspires a little bit more to this than other labs. Brookhaven is, as you said, we are situated in New York State on Long Island. We are just over 75 years old, have been here for a long time. We sit on about 5,000 acres. We have over 300 buildings that we maintain, so we're a little science city here out on Long Island. The main focus of Brookhaven is really large-scale experimental facilities. Those include one of the latest news that was out there is we just got awarded the build of the next electron-ion collider. That is a unique research facility for the high energy and nuclear physics community out there. Worldwide collaboration in building this, and this will have really a lot of exciting opportunities for computing as well involved from the design stages onwards to the build and the operation. We also currently operate the Relativistic Heavy Ion Collider, a nuclear physics experimental facility with worldwide users. We have the newest synchrotron in the US, the National Synchrotron Light Source 2, which is the brightest light source in the US. That's really focused on research, materials research, chemistry research, and biological research. The NSLS2, as it's shortened, was used, for example, in part for the development of the COVID-19 vaccine by Pfizer. So those kind of things we're doing. We have a Center for Functional Nanomaterials. We have a number of climate facilities that we are involved in, the atmospheric radiation measurement facility from BER. And then we have, for example, the isotope production facility on site, which we're very proud of. They produce medical grade isotopes that are particularly useful for cancer treatments, for example. And then we have really interesting facilities like the NASA Space Radiation Lab, where we test equipment for NASA and other industry and other researchers that need to go into space and to see if they are hardy enough to work there. Giving that background, so when DOE started to get more interested into quantum, we really looked at what expertise do we have on site. There's obviously a lot of high energy and nuclear physics expertise. We're, for example, also the Tier 1 Center for the LHC Atlas experiment. And we have a lot of material science research. And so the question was, how can we leverage what we do already and translate this into quantum and really make a difference in that area? And one of the first areas that we really focused on was quantum networking. And Gabriella can talk more about this later, but we brought our traditional networking expertise that we had in CSI, for example, together with the expertise that instrumentation has in building new capabilities and the expertise of our physicists to say, okay, how could we create a quantum internet? And you might have seen this. We actually organized and hosted the workshop that developed the quantum networking blueprint in New York, which is now used everywhere to say, okay, this is how we go about it. And we're sort of gradually progressing along that. Another key area was certainly for the computational science initiative to say, okay, we have a lot of applications. We have focused specifically on artificial intelligence development for our facilities, but also for exascale computing here. We have Meifing and her team working with a number of applications in physics and in chemistry. And so the question is, how can we take this expertise and bring it into the quantum world? And so we work there quite a bit. So we have a large area that I'll talk about a little later in quantum machine learning, for example, but also the application of traditional machine learning to quantum technologies to see how we can optimize them. We have a lot of understanding here on programming models and compilers, and combining that with the physics knowledge. I think Meifing can talk about some of the exciting things that we've done there in optimizing gates and optimizing compilers and what we can do there. And then we have obviously our colleagues at the light source and in some of the other departments that work on material science, improving materials, designing new materials, and they are involved in another really exciting area. So Brookhaven is leading one of the 5 quantum centers. Ours is the one for Center for Quantum Advantage, C2QA. And that is focused really on how can we optimize the whole stack from the materials up to the applications to build quantum computers that are useful, that are more resistant, not as error prone as they are. And what Brookhaven brings in particular to the table is here the materials knowledge on how to create new qubits that have longer coherence times and less errors. And probably Gabriella and I will talk a little bit more about that later. So that's sort of in a nutshell.
That's excellent. Sets the scene quite well for us to drill down. When we look at the quantum science, quantum technology landscape as an analyst firm, we see it as quantum sensing focused on measurements, quantum communication focused on quantum networking and propagation of data, and then quantum computing, where we would, in a programmable way, manipulate probability functions. And what gets superimposed on this, especially in the HPC world, is the quantum inspired algorithms that may be running on classical systems and run quite well, but also inform a different way of thinking about this. If you would comment on that, whether you see it the same way and how you might modify it, that would be great. And then I have a follow-up question, of course.
So we also have some work in quantum sensing. What the particular aspect that we are looking at is how we can connect those sensors through quantum networking to really improve the sensitivity of measurements that we could create in the future. And we have an effort there in astronomy, for example, that's looking at that, but also in other areas. So I think that's the slight tweak. And then when we look at algorithms, we are looking at really making sure we don't just want to run the same things on a quantum system. There has to be a benefit to it, a real quantum advantage. And I can talk a little bit about that in the context of AI. But the other thing is that, yes, we had some of our theorists around the side look also at, are there things in particular in nuclear physics that you can't calculate today? It's just the power is not enough of exascale systems or anything that will come in the near future to calculate certain aspects, and targeting those with new quantum algorithms is another key focus for us.
That's a really good point.
How far away from being able to do that with quantum would you say we are?
So certainly on simulators, we've demonstrated some capabilities that allowed us to calculate things that weren't possible on classical computers. But for the more complex theories, we just need larger quantum systems to really make a difference. I don't know, Gabriella, if you have more to add to that.
So I may add something more about the sensing part, perhaps, in that we look at 2 different ways to develop quantum sensing. One, which is really directly quantum sensing, using some of our systems which help to intrinsically push the sensitivity for fundamental units like magnetic fields and a very low level, because you can develop a very sensitive system. And the other one is more like what Kerstin had said, which falls more in the category of quantum enhanced techniques, where you use some of, for example, entangled pair distribution approaches to improve the resolution, for example, in some of the quantum astrometry applications, but also on quantum LiDAR, where your quantum enabled systems can improve at the end of the day the resolution, but also the distance you can cover. So it's an adoption of quantum principles to more standard techniques. And we're also doing that, for example, in a very difficult domain, which is X-rays. So we are working also on quantum X-rays microscope, which will sit hopefully at NSLS2, where the system will use an X-ray entangled pair photons to improve the contrast of the images from very weak samples, which then can, provide a good resolution without suffering the damages of too strong X-rays.
Very, very impressive. So thank you for that. Maybe if we can, take us to quantum networking, quantum communication 101. When we talk about quantum communication networking, our mental image is the traditional networking that we have with electrons going through pipes or, radio waves going through the air. Quantum communication, how does that work at that basic level? What is the fundamental method of transmitting information from point A to point B that is different from traditional ways?
So I would say it's not really the medium that makes a difference. You still have to use classical vehicles, which are like, photons, or, which travels in fibers or in air, right? And we are working on both ends for a land-based and a free space-based communication. Obviously, they are mature at different levels. The significant difference is really what you transmit and how you have to handle the photons you transmit to maintain, the entanglement between the pair and ensure that you can keep propagating that type of information, knowing at each point what you're sending without destroying, which is a key point on quantum information, right?
Right.
So that is the very main difference. You have a different source of information. So say you can have a source that generates entangled pair of photons, and then you transmit those. You need to work with them in a very different way because, again, intrinsically they cannot be treated as a normal classical information. And in addition, I think there are two key differences, for example, which are the main area of research in these days. And they are critical in that one would really help to extend the distance we can cover. And that is the equivalent of when you have your repeaters, right? So in classical communication, you have a point where at some point your signal transmitted in the fibers gets absorbed, becomes very weak. You need to detect it and regenerate it. Now, you can't have the same approach in quantum because you can't really detect and regenerate. So there is another way to go around it. Actually, there are different methodologies. People are working and trying to develop what is called the quantum repeater. The quantum repeater would be really one of those key enablers to extend the distance we can cover with quantum communication. And another aspect a bit lower in terms of starting with the communication is really how you can connect the different quantum devices to your network. Say, as we do, we want to use an existing network of optical fibers, which are the same that we use for similar, let's say, or at least they are available to lease from company. But you want to have your quantum device that can put up an information at that level. And that has a specific wavelength that allows you to cover a given distance. And obviously, not all the quantum systems, actually, I would say none of the quantum systems start with that. So you have to make an additional step which allows you to move, say, for your system, which say generate polarized photons which contain your quantum information at a wavelength which is not optimal, and apply some nonlinear optics tricks to move that to the right wavelength. That's one case where you do from optical to optical. Even a bit more complex is the case where many of the units or qubits that we read in the news are superconducting, right? They live in this big deal fridge, these big chandeliers. We see all these photos in the news. And all that is in a completely different regime, which is microwave. So in that case, you need to move from microwave to optical, and you have to transduce this signal, and that is another challenge many researchers are working on. But the idea is we are creating this concept of network that would allow different type of technology to plug in and then being distributed and utilized for different applications. Obviously, there are several possibilities at that point, and maybe I can continue going to that later.
When you hear quantum communication, what you envision is that you've got some kind of an entity, a photon in New York, and you've got another one in London and they are entangled. And that's how you do the communication, that the state of the guy in New York impacts the one in London, and you read it over there. To what extent is this a valid mental image?
It is as implication as it would be in the case of the real classical communication, right? So you think there's one point to point, but in reality, it's a graph that we define in the quantum communication, where we generate an entangled pair, and then we have a series of swapping station, and then eventually you find your path from point A to point B. So it really the development of a graph in the pure network sense of view, which is a symmetrical type of multi-node system, which will connect you from the point that you have in mind.
I see. Now, you also mentioned swapping station, which also indicates that unlike traditional networking, when the data gets copied, in
Yeah,
quantum communication, there is no copying.
that's exactly what I was saying before. That's one of the main differences, right? There are buffers, there are swapping. You have to be very careful on how you approach that.
A world with a quantum internet, what would that be like? I mean, are we just talking faster? Are we talking more secure? From the perspective of the non-quantum person developing this kind of thing, what would be the purpose of this quantum internet? Would it enable all sorts of new workloads and applications, or what would the impact be?
Right. So I would like to be clear. There isn't such a thing as faster than light. So we use light. That's the speed we can deal with. So let's put this to rest. But in terms of capabilities, security is intrinsically built for the very same reasons we discussed earlier, right? So you cannot just snoop and not impact the photons that you're trying to move. Obviously, in addition to that, once we are developing a new system, we will be thinking about how to ensure that security is maintained. So security is really a key element, and I think everybody today is very sensitive about secure communication. So there is that, but also the type of information we send. There is a possibility to have a very dense information in the qubit, the very same way you do think about quantum computing in terms of information handling. There are also some derivative in the way you develop a system which requires a lot of coexistence between classical and quantum, and that helps to really also improve some precision, timing, and other characteristics we try to exploit in communication. One major element I think it's very important to keep in mind is that I personally believe that the network, the communication, is really a key element for the advancement also of quantum computing, because you may think that at one point you may have some limitation on how big a qubit system can be, but the way to go beyond this limitation, it really is to think about multi-node quantum computers. And in order to do that, you really need to connect the different nodes. And connecting different nodes of processing units is part of what a quantum network can do.
Very good.
One other question is talk about this melding of classical and quantum that, for example, Meifing was mentioning. We're kind of in this transitional role, and I think it seems to be generally accepted that quantum will be kind of an accelerator sitting next to and augmenting classical in the future once quantum really reaches a higher level of maturity. But that whole transition between the two, and we'll end up with applications weighted toward one or the other. Is that how you all see the future looking out, I don't know, 10, 12 years from now?
Yes, I think that's how I would see the role quantum computing is. So it's unlikely that quantum computing will replace everything we do right now, right, on the classical PC systems. But there are certain problems that we can't solve, so they are intractable with the classical HPC. And those problems are the type of things we can solve with quantum computers. For example, Kerstin mentioned earlier some nuclear physics problems that are too hard to be solved on classical computers. And one of the problems is this infamous sign problem, right? So it's mathematically impossible to simulate, for example, QCD, quantum chromodynamics at high density. But this is something that quantum computers may be able to solve when we have large enough scale quantum computer. So so I think I agree. Quantum classical hybrid approach may be the future of quantum computing.
Now, that, of course, also immediately brings HPC into the quantum science market because, as usual, HPC tends to be the early adopter and finds really good uses and starts having an impact on the development of that science altogether. What other applications do you see besides quantum physics, QCD types, that you feel are eligible in line? What would come after that?
Well, I think maybe even well before that, we have had a number of projects where we used quantum artificial intelligence,
Mm-hmm.
quantum machine learning. And even with the existing systems, we could already demonstrate a clear advantage of using quantum computers for key workloads, for example, for some of the high-energy physics experimental facilities and their data analytics that they're doing. What we found was that the quantum machine learning algorithms not only converged faster than classical ones, but they also delivered better results. So there's a real advantage there that we want to leverage as soon as possible. So applications like that. The other thing that we've done, Gabriella mentioned this already, there is an increased interest in secure computing and secure networking. And in particular as part of the energy infrastructure. And so we had developed on the classical side privacy preserving AI, as it's called, basically, where you can see neither the data nor the algorithms if they are run on public computers. And obviously, given the nature of quantum networking and computing, that seemed an ideal thing to port over. And so we've done that as well and showed what you can do with it, that you can achieve the same results, but with an even higher level of security. So I think I could see those kind of applications also making use of quantum computers once they become a little bit more stable.
Would you put that in the more general category of confidential computing, or would it
Yes.
be beyond? Yeah, okay.
Could I ask too, just as an aside, and tell me if this is an unfair question, but what quantum computing hardware or platforms are you all using? Is it an in-house developed kind of capability or one of the vendors or?
So we have actually access to quite a number of systems. So we have subscriptions as Brookhaven to the IBM Quantum Hub system so that we can get access to their largest systems and have dedicated time. We're also using the Oak Ridge service that gives additional access, but obviously there we compete with others for the queue. So our dedicated queues are quite important. And then we have collaborations with the Googles and Amazons of this world and get access to some of their systems. And we have connections to universities that give us access to. So in particular, in the quantum machine learning area, and I think Meifing as well, we've been able to access quite a number of systems and test our algorithms across this broad spectrum of systems.
When you look at those platforms, are you generally impressed with their level of capability, or do you think things should be further along by now, or what is your sense of the progress being made?
No, I mean, would we like to have larger systems? Would we like to have systems with higher coherence time? Absolutely, to help our science. But if I look at the progress that has been made in a short time, certainly when I think of IBM, how much their systems have grown, how the concepts are changing from one monolithic system now to federated nodes, that's really exciting. And I think it's, if I compare this to HPC, it's quite rapid progress as well.
Fascinating. Yeah, we certainly we hear lots of great announcements coming out of IBM, and it seems really impressive. But it's Shahin, it's really nice to hear that from an actual end user.
Absolutely. Yeah. My view has been that they've set up a very ambitious roadmap and they've been executing pretty well. And I also give them good marks for their hub and their cloud and their open source and community development. Really a good job there. And of course, as you mentioned, the whole industry is making rapid advances, I would say primarily with the supply chain, but also with the actual systems. So there's a lot of hope to make it into production soon. I guess one, final question for me is really the development environment for quantum networking and quantum computing at the control level, at the kernel level, at the application level. What is your perspective on where the industry is at and what it needs to do?
So I think Gabriella can talk a little bit about quantum networking, where we've basically developed those control layers. And I think we're doing pretty well, although taking this all the way up to have an environment where people can program their applications, I think we still have a little bit to go. For the quantum computing, certainly with the IBM service at the application level with the Qiskit, that has been very helpful, in particular as Qiskit can be used to port applications to different platforms as well. So I think, Meifing, you've worked at much deeper levels with those systems as well, and our access to special queues for that has been quite helpful.
Yes. So the IBM Qiskit library provides a lot of functionalities, provides a lot of knobs for us to tune, right? And in terms of low-level control, we were able to basically use their APIs to do some experiments to see how we can improve the gate errors with the same hardware, right? So because the different control pulses will affect the gate errors. So I think it's maturing, but there's still a lot of research to be done.
So if you look at photonics, electron, atom, ion, superconducting, topological, all these other different approaches to quantum computing, is it too early to develop a feel for what is likely to be the winner, or have you already formed some opinion?
So I don't think there is a winner yet. I have the feeling that this dates me, this might be a Betamax VHS situation. Where not necessarily the best technology, but the best marketing wins.
That's an excellent point.
So I think we'll have to see what comes out. So it will be interesting to watch what will survive.
Excellent. No, I think you're right on. You're right.
Yeah, it's such a decentralized global thing that's working on so many different levels, different areas, different companies and all that. So you're right. I mean, how it all comes together at some point will be a fascinating process. Well, it's been a real pleasure speaking with the three of you.
Absolutely. Anything we didn't ask or any comment that you'd like to make?
Well, I think thank you very much, first of all, for giving us the opportunity to talk. I think speaking for my colleagues, we all very much enjoyed this. The only closing thing I would like to say is that at Brookhaven, we're always open to collaboration. So if you want to work with us, please do feel free and contact us. And in particular, when it comes to quantum networking, we actually have, I think, a worldwide unique quantum networking testbed facility. So if you want to try out your application, your tools, you can do that there without having to set up your own network. And that might be quite interesting to listeners as well.
That's absolutely brilliant, and we will amplify that. So everybody, go take advantage of this, because I think the range of scientific activities that you described is so broad and so interesting. Really, if I lived within 100 miles of you, I would want to visit every day. So.
We've been with Kerstin Kleese van Dam, Gabriella Carini, and Meifing Lin of Brookhaven National Lab. Thanks so much.
Thank you very much.
Thank you.
Thank you for making the time. And I really look forward to continuing this conversation in a few months, or when you have a good milestone that you'd like to share. Please do.
Thank you.
All right.
All right. Thank you.
Bye.
Bye.
That's it for this episode of the At HPC podcast. Every episode is featured on InsideHPC.com and posted on OrionX.net. Use the comment section or tweet us with any questions or to propose topics of discussion. If you like the show, rate and review it on Apple Podcasts or wherever you listen. The At HPC podcast is a production of OrionX in association with Inside HPC. Thank you for listening.